Now the PDF?
Yes.
Now the PDF.
And
Yes, it looks like we can. Yes, we got it.
now the fractal?
Yes.
Okay, all right. So PDF. So okay. So last time we started talk about the fractal, right? So what is the one thing struck you as what do you remember about the fractal?
Self-similarity.
Self-similarity. So that's one self-similarity. What self-similarity means?
You take a smaller, like you take a smaller specific, like, I guess just like qualitatively, if you take like a smaller series of iterations, you can expand it back up into its full thing.
So it's one thing to say it's a similarity on all the different scale. It's also get the complexity at all the scale. So it's complexity in all scale. Namely, if you go to smaller scale, it's manifest as much complex as in larger scale. That is more general speaking. And the complexity or the pattern or the objects look similar at larger scale, at smaller scale, and similar to the larger scale. And we started using a simple example of well, we start with talking about the countable and uncountable object. So what is countable means?
So a set is countable if it has the same number of things in it as there are natural numbers.
Okay. Yeah, I think that's right. But I guess the same number of things maybe it's harder to define, to say what it means by same number. There's more precise definition, say it's the same number as in the integer. What is a more precise definition?
The cardinality is the same as the natural set.
How you define cardinality?
You can enumerate each element.
Yes. So
that's a one-to-one relationship.
Yeah. So the key thing is that you're able to map one-to-one into the standard countable set, which is the whole, which is natural number. Namely, you can arrange the things in a sequence like 1, 2, 3, 4, 5. That means that you can map every member of the set into 1, 2, 3, 4, 5. So they have unique one-to-one mapping. And so as long as you can find such one-to-one mapping, then we say set is countable. And then we talk about, so natural number is a countable, integer countable, even number countable, fraction number are countable. Then we started introducing the Cantor set. Now you remember how the Cantor set is constructed, right? It started with a unit length between 0 and 1, and we cut 1/3 off in the middle, and then we repeat. So Cantor set clearly is a fractal because it's a complexity. It doesn't matter how small scale you go, it gets its complexity. And then of course it gets a strict exact self-similarity. Namely, if you reduce the length scale by 1/3, the object look exactly as the larger one. So you have exact self-similarity. So that's the Cantor set. Cantor set also has a interesting property to say it has 0 measure. Namely, its total length is 0, but the number of elements in the Cantor set is uncountable. Namely, it's a lot more than just a whole number. So it's a 0 set and uncountable. The way we show that it's uncountable is by self-contradiction, namely by constructing, assuming that it's countable, and then we can construct a particular number which is in the set, but which is in the Cantor set, but it is not mapping into possible arrangement, So that's how we construct it. Now we say a key measure of this fractal is self-similarity, and so we're going to introduce a dimension to measure this fractal. So we're going to talk about primarily the dimension. So the dimension of fractal, and then there's actually several ways of defining a dimension. Now, for object which has a strict self-similarity, it's actually very easy to do that. We define a dimension called self-similarity, a self-similar fractal. So let's take this a simple example of when Kopf curve, which is defined a little bit similar to the Cantor set, but it's actually going other way around. So we take a segment, let's say between 0 and 1, right? Between 0 and 1, and then we divide it into the 3 segments. So 1/3, 1/3, 1/3, and then in the first iteration, we take the middle 1/3. Instead of cutting off, we make it to a triangle. Okay, so replacing the middle segment by 2 segments, which is has exactly the same length, but length is going up by 60 degrees. So this is a equilateral triangle, but except we remove this part and then replace by these 2 segments. Is that clear how this iteration get done?
Yes.
Okay. So once we have that, then the next iteration we just repeat the same thing. We take every segment, we replace by this segment. So if I call the initial segment length 1, what will be length of the new after 1 iteration?
4/3.
4/3. That's right. 4/3. So, and then after the second iteration, the length will be taking the length of S1 and then multiply by 4/3, right? So, because each of these elements now replaced by a 4/3 of in terms of total length, right? So, as we see, we're going on here. Every iteration, the length increased by 4/3. Right? Is that the kind of obvious now, right? So going from here, the length now increased by 3. This actually is a very simple model of a coastal line. If you look at the very high level, namely a ruler which is very long. Let's say you measure the coastline in terms of a mile. You know, you take a ruler which is a mile length, a straight ruler, and then you measure your coastal line, you probably get a certain number of mile. You get a number. So like this. So let's say this is 1 mile, for example, and then you measure the coastal line into 1 mile. So on this length scale, all kind of this detail disappear in the coastline. But then if you using a ruler scale, which is 1/3 of a mile as a basic unit, then you see a little bit complexity. So now that coastal line becomes 4/3 of a mile, okay, 4/3 of a mile. And then if you take 1/9 mile as your ruler, okay, now your coastal line length is 4/3 to the square. So now it's significantly larger than 1 mile. And I keep going on. So now instead of using 1 mile, maybe you're going to using either smaller ruler scale. So as your basic measurement units getting smaller, the length of this coastal line actually increase. So we can mathematically, we can literally show how this length, right? So that the length, in fact, this K in the length actually go to infinity. The K has infinite arc length, this Kopf curve. So even though it's a finite size, you know, if this is actually everything confined between 1 to 1, okay, between 0 and 1. and the height is no more than 1/3. So it is a line, but it's which is a finite, occupy finite space in a dimension wise, but its length is infinity. It's infinity as you go to iteration, keep going. So in fact, the length at nth iteration is 4/3 to the nth power of L0. Now we can take L0 equal to whatever number, but L0 can be taken equal to 1, right? So if you zoom in every small bit of this curve, in fact, every of this small bit is infinity length. And of course, if you take this segment, zooming out by 1/3 or by a factor 3, it will look exactly the same as the larger object. So this has exact self-similarity. If we take this part and zoom in, it will look exactly like this, So we can then define a self-similarity dimension. So this is the object clearly is, in terms of dimension, is bigger than 1. But of course, it's not 2 because it doesn't occupy whole 2 dimensions. So it has a dimension somewhere between 1 and 2. And then we can define that in terms of self-similar, using a dimension called self-similarity dimension. So the idea of self-similarity dimension is the following. If I have an object, okay, if an object, let's say, consider a square region, okay, which if I using a ruler which is r equal to 2 to measure it, okay, let's say this ruler, a scale factor r equal to 2, then maybe we divide this length into 2, so therefore this length is 2, this length is 2, then we count how many square, we have 4. But if we use a scale which is a 1/3, namely, then of course we divide this side length into 1/3, 1/3, 1/3, 1/3, 1/3 length. In the 1/3 units, the number of the square here is 1/9. It's a 9th. So if you're using half of the length as a measure, then I get 4. If I have a sorry, that's me just. I need to turn this off. So why is my public radio? Since okay, I hope that it's off. So if I use a 1/3 as a basic unit, I get 9. All right, so let me turn the phone off just in case I'm going to disturb. So if we shrink the factor 2 into direction, it takes 4 of a small square. If we use shrink by factor 3, we get 9. So we can define a similarity dimension D, okay, which is to say, if I change the scale by factor R, how many number of units I increase by matching M. So M equal R to D power. So if we're using a factor 2 to count, we get 2 to the 2. In the case of simple 2-dimensional object, we get 2. 2 to the 2 square, we get 4. If R is 3, we get 9. So with this D is, of course, log M log R. So suppose that a self-similar set is composed of M copy of self scaled down by a factor of R, then the similarity dimension D is defined by this relationship. So by this, and therefore D is log M and log R. Now using this rule, so if we have a straight line, we cut into half, we get 2 pieces. So therefore, if a straight line if we reduce the scale by a factor of 2, we get 2. If we reduce the factor by 3, we get 3. So straight line we have dimension equal to 1. If a square, solid square object in 2 dimensions, you get 2. Now using this, now we can let's say measure the Cantor set. For example, Cantor set. Cantor set is we have segment which is 1. We reduce the scale by factor 3. We eliminated 2. We made the middle half. So we left with 2 objects. So we reduce the factor by 3. We get the 2 objects. So therefore, according to our self-similarity dimension definition, Cantor set has a dimension which is log 2 over log 3. And you see this number is less than 1. So Cantor set has a dimension less than 1, because 1 is a continuous line, and the Cantor set is not continuous line. But it gets a finite dimension. The dimension is not 0. The dimension 0 will be just a point. So in fact, a countable object has a dimension 0. Has dimension 0. Okay. So anything which is uncountable has a dimension which is finite number. So Cantor set has a dimension with 0.63. 0.63. Now you clearly can construct a object anywhere like a Cantor set with a dimension anywhere between 0 and 1. It's very easy to do that. So you basically divide it into many segments and eliminate some of them. If we apply same notion of self-similarity dimension to Koch curve, Koch or Koch? Koch. How you pronounce this?
I think Koch. I'm
Koch?
not sure.
Anybody want to chime in? What do you think is pronunciation? Koch curve? Koch curve. I think that was, when I was a graduate student, there was a mayor in New York City. And they usually TV say Koch. So I don't know. Koch? That definitely is not Koch. Koch curve. So this object, right? We reduce the scale by a factor of 3, and then we get 4 copies of itself, right? So therefore, dimension is log 4 over log 3, and this dimension is slightly bigger than 1. So Koch curve has a dimension which is larger than 1. That's why its length is infinity. Anything which is dimension which is larger than 1 is a finite size, but has a length which is go to infinity. Okay, 2-dimensional objects, you cannot measure in length. In the measuring length is go to infinity. Right. So with that, then we can generalize to much more general Cantor set. For example, here is a Cantor set, which we reduce the scale by a factor of 5, 1, 2, 3, 4, 5, and then we eliminate 2 world length. So what will be the dimension of this object? Ray? Are you there?
Yeah.
What is the dimension of this object?
This only 1?
Is 1?
Wait. It's not.
I think, okay, since there's 3, well, actually, each iteration produces 3 copies and they're reduced by a 5th, right? So ln3, ln5?
Yeah, it's a log 3 over log 5. That's why we reduce it by factor 5. We get 3 copies of itself. So it's ln3 over ln5, right? ln3, ln5. So that is ln3 over l5, right? And so set S is called topological contour set. So so S is a total disconnected, just like Cantor set itself. It's as interesting. It's total every point of there. When we iterate this to infinity, remember the set is defined is not at a certain state. The set is defined by this angle to infinity. It's okay. So it's a total disconnected. It's contained no isolated point. So that's very interesting. Everybody is disconnected with everybody, but none of them is isolated. It's like, you know, physics 594 class now. We all are isolated from each other, but we are all connected in certain degree. So this is a topological feature of this now. So this is one way to calculate dimension. If the object has okay, we are back.
Yes.
I think my internet connection has not been stable. I have noticed this for the last week. Just too many people using it. Now, so do you lost the screen? Do I need to share the screen again?
Yeah, you're gonna have to do that.
Okay, let me share. Do I able now switching back and forwards?
We got the
What do you see?
the PDF right now.
It's just PDF. You don't see the Cantor set.
No. Well,
No.
well,
Yes or no?
Oh.
well, we see the PDF about the Cantor set, but not the.
Wait a second. I don't have PDF of Cantor set.
Well, like this, we got the PDF of the book, but we don't see any like Jupyter Lab notebook.
Now?
Okay, now we see it.
Yes.
Yeah, we got it now.
Okay, so I'm switching to the Jupyter Note and showing some example, more example of fractal. I'm going to talk about it, Julia set and the mental set either later or next lecture. But first, I have this more fractal. This Pinsky triangle. Let me run this code and to see. Also, I still have this bug which I don't know how to fix. If you guys, any of you can spend some time on this thing to fix this bug. So the first time I run it, it doesn't work, but I run one more time. It's showing up. So I don't know why, and I couldn't figure out how to fix these things. Now this is a second iteration of Sierpinski, sometimes referred to as Sierpinski gasket. Okay, so I don't know whether you guys understand. Did you see that animation when it happens?
Yes.
Yes.
Okay, so what I do is I take a triangle, all right? Take a triangle, and then reduce the scale factor by 2. So every edge is now half. So therefore, I generate 4 equilateral triangles, right? So I get 4 equilateral triangles. Are you guys hearing me?
Yeah.
Why my
It cut out for me.
why my internet showing up say I'm on airport mode? I don't understand that. Airplane mode. Are you guys still hear me? It looked like I may lost somebody. Some of you.
For disaster.
This seems is unstable. Are you see? Are you?
We can see now.
You can see it now?
Yeah.
Okay. So let me see what I can run one more time again. So I need to run twice to run it. As I was saying earlier, say if some of you guys can look at my code and see where's the bug and fix it, I'll be appreciated, but I couldn't figure out how to fix it. So we take a triangle, right, a big triangle. We use a factor of a reducing factor by two. So we draw now 4 equilateral triangle. Okay. And what we do is we eliminate the middle one, eliminate this green one, right? You all see that?
Yes.
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 And then I repeat the same thing. Now take a smaller triangle, do a factor 2 scaling. I get 4 equilateral triangle. Again, eliminate the middle one, which is now is a red one. Okay, the red one. So I just then repeated this process. So then let me run this code. Instead level 2, I get level 4, let's say. Let me run on level 4. I need to run twice. Now you see this. Anyway, so this is a level 4 iteration. So as I keep doing this, and then you can imagine you go to infinity. So my question is, what is left? Is called Sierpinski gasket. What is the dimension of this object for Sierpinski gasket? What is left over here? I'm gonna call Brian.
Let's see. So it would be 3 copies. So is it log? I want to say log of 4 over log of 3, but I don't think that's right because that's what the other thing was.
Why you think it's not right? Right. So
wasn't that what the von Koch curve was?
Yes. Von Koch curve is log 4 over log 3.
Yeah, which is why I don't think that I'm right that this one is log 4 over log 3.
But this one is also log 4 over log 3 because I reduce a factor by 2. Right? It's a factor by 2. I get, well, it's not log 4 over log 2. I reduce factor by 2. How many copy of itself we get?
3.
3.
So therefore, this dimension of this one is log 3 over log 2. Okay, it's not log 4 over log 3. It's log 3 over log 2. Everybody get that? I reduce a factor by 2. So from 1 copy, if I'm using now a factor 2 scaling, then I get 3 copy. Right? I use a factor 2 scaling, I get 3 copy. So therefore, the dimension of this thing is log 3 over log 2. You agree?
Yes.
Yeah.
Yes. Okay. Let's do a little bit more. I have another screen here. Here is another website. Let's say this is called Snowflake. Snowflake. So here, let me run this. Oh. Now, this object, if I go to smaller scale, what will be dimension? Matthew. You there, Matthew?
Sorry, you're cutting in and out. So you're asking about the dimension of this object?
Yeah. Are you seeing the snowflake?
Yes.
Yeah. Okay. Yeah, I'm asking the dimension of this object.
So here you're not making any copies of the same object as you're going down. So I would guess that it would be the same dimension as the Koch curve.
Yeah, as a Koch curve. Yes. Well,
right.
so if you look at segment of this things, which is basically, it started with a triangle. It started with triangle, right? And then you replace each of this triangle with another. It's just like a Koch curve. Each of this segment is now factor 3, and then you get 4 copies cell. All right, 4 copies cell. And then you repeat it for every segment. You repeat the same. So for the segment, as far as segment concerned, is the same as a Koch curve. Koch curve. So therefore, this object has a dimension log 4 over log 3. All right, it's just a little bit larger than 1. Let's go to the next one. Can you see that? Can you see how this object is generated? That's an animation of this, right? It started with a line, a square box line. Every side now is replaced by, actually it's not clear. How is every side is replaced by itself? This is a little bit, even me, it's a little bit difficult to see. Let me skip, let me see with animation showing up any better. No, this doesn't do any good. Let's see what the next one. This one. Anybody can calculate the dimension of this one? I'll give you a few minutes. Each of you calculate a number and then shout it out. I'll do it myself now. You're seeing the animation, right?
Yes.
Yeah.
So stay up that animation and see how it get every segment is get replaced. If you get a number, you shout it out.
Honestly, I can barely even tell like the pattern.
Can I?
Like I don't.
Same here.
It's like real hard to like.
It's really hard to see the pattern.
Yeah, because like you got that first little like line pointing inwards to the center of the center of the square, and then like 2 more lines appear on that. Like,
See what I can do. The simulation, was that a little bit clear? This is a static picture.
yeah, that actually might be a little bit better just because, you know, it's not moving.
So as I understand it, every iteration you're adding these spikes that come out
Yes.
of each line, And so for each line you add, or at least the ones in the center, you add 2, and each one of them looks like they're 1/3 of the original length. So I'm thinking it would be log 2 over log 3.
Log 2 over log 3? So okay, so if you look at the center one, if you look this, you're replacing one copy with 1, 2, 3, 4, 5 copy, isn't it?
Well, on the first iteration, you only add the 4 like long ones in the center, right?
Yeah, so in terms of length, then if you take this one segment originally, right? You reduce by a factor of 3, 3 segment, but now you have one additional, so you get 4 copy of cell. So if you look at the side, I get 4 copy cell. It's 1, 2, 3, 4. So it seems to be will suggest log 4 over log 3. But then if I look at this segment iteration, it seems to be get 5. So it's 1, 2, 3, 4, 5. I get 5 copy cell when I reduce by a factor of 3.
Could the issue be that this isn't self-similar?
So this
Unless
is
I'm
not
missing
this is
something,
not
right?
exact. Yeah. So this is a case where it's not exactly self-similar, right? So this is the case where it's not exactly self-similar. So the dimension is a little bit hard to define because it's not exactly self-similar. It's similar, but it's not exactly self-similar. Right. So I cannot say I do a factor of 3 and then I get exact copy. So it doesn't get exact copy because it's missing this line, missing this line, missing the middle line. Okay, it's missing middle line. Okay, so and then so this suggests we need another way of define a dimension. So when the object which does not have exact cell similarity, we need a different way of define dimension. Same thing with this things, with this object, for example. So it's not exactly cell similarity. Right. So that's then let's go back to the definition of cell similarity. Are you seeing back to the PDF file?
Yes.
Yeah.
All right. So now we're introducing another way of defining dimension called box dimension. Okay. A box dimension is for an object which doesn't have to be exactly cell similarity. So we say for the object, one can imagine we're covering the set with a box of size epsilon. So if our object are using the size epsilon to cover it, we say how many boxes we needed to cover this object. So if it's a simple line, a continuous line, a smooth line, then if I'm using epsilon to cover it, I said certain number of box, and so number of box need to cover line. Okay, it's simply just divide length divide by box. So if it's 1 dimension, if it's 2 dimension, of course, object in 2 dimension, how many box of size epsilon square I needed? It will scale with, so basically take an area of the box. If it's 2 dimension, take area divide by epsilon square, and that will be number of box. So number of box need to be scaled up with epsilon to the square. Well, with 1 over epsilon square. So a line will scale with 1 over epsilon to 1 power. A area will scale with 1 over epsilon to the square. So so here's a formal definition that S be a subset of n-dimensional Euclidean space, and that n epsilon be minimum number of d-dimensional cube of the size epsilon needed to cover S. How does n number of box scale with epsilon? And for general fractal objects, this ne will scale is 1 over epsilon to the dth power. So that give us a definition of the so-called box dimension. So box dimension is the limit on number of box I need to cover if the size of box is epsilon. So D is defined as log n e over log 1 over epsilon. So for Kafka, you know, we are the epsilon will be 1/3. 1 over 1/3 it will give you 3. So here's a log 3 denominator, and the number of box is log 4. So it's the same thing. So for the object which has the exact set similarity, the box dimension is no different from the set similarity dimension. But this is now a little bit generalized for object which does not have the exact set similarity. So in the case of this is in case of Cantor set, for example, we are reducing epsilon is 1/3 every time we go to iteration, but number of box we need to cover it is 2 twice. So therefore it's log 2 over log 3. Now here's an example of a generalization of Sierpinski gasket to not exactly set similar. So I started with a square. Okay, I started with square. I use a factor of 3, so therefore my epsilon is 1/3. So 1/3 of length scale using my epsilon. And notice that if it's strictly 2 dimensional, I get a 9. I get 9. But I randomly pick one of length and eliminate. So this is in this case it is a square. So that's the first iteration. Everybody is clear how this get done?
Yeah.
Okay, now I repeat this thing for the smaller box. So I take this smaller box, using scale is 1/3 of that. Again, I get 9 box. I randomly eliminate one length. So you can see this, in this case, the center one get eliminated, but for this case, I get size because it's random. So it could be any of those 9 get eliminated. So here is this one eliminated, here, this one eliminated. This, in this case, I get this corner eliminated, so on and so forth. So you can see on close scale, on average scale, is repeat itself. So on average, this object repeat itself. Basically, every one of this box, one of the 9 box is eliminated, but it's not exactly repeating itself, right? So therefore, in this case, I using factor epsilon is 3, namely 1 over epsilon is 1/3. 1 over epsilon is 3, but I only need 8 box to cover this object. I need 8 box to cover object. Okay. So what will be then using this box dimension as a definition? What will be dimension of this object? Here, what will be dimension of this object?
The one on the left, right?
Well, let's keep iterating to infinity. Then I get this object. What will be dimension of this object?
Thing is natural of 8 over 1, 2. Natural log of 3.
Yeah, so it'll be log 8 over log 3. So it's almost 2. You can see that it's almost 2, but it's not quite 2, right? If we didn't eliminate this box, then it will be log of 9 over log 3, that will be 2. That's strictly 2 dimension. But every iteration we eliminate one of the box, 1 out of 9. So therefore it's log 8. This will give you a dimension which is log 8 over log 3. Log 8 over log 3. Okay? So here, this will be log 8 over log 3. Because my epsilon is 1/3, 1 over epsilon is 3, but number of box I need to going up is by 8. So this is the box dimension. Now the box dimension then is slightly more general than the self-similar dimension. So you can use this to measure the object which is not exactly self-similar, but approximately self-similar. And then you can just simply use in box to count similarity. The problem with the box dimension is it's easy to visualize, but actually it's very difficult to calculate itself. Because when you go to things, go to smaller scale, how do you know how many exactly box? If you don't know the rule, it's kind of hard to, like the chaotic region of the logistic map or the chaotic attractor of Lorentzian map. We don't know exactly what's the underlying rule, how to get it generated, right? So it's difficult to calculate in practice, even though intuitively it's easy to see. So finally, we come to the definition dimension called correlate dimension, which is easy to implement numerically to calculate. So called point-wise and correlation dimension. So here's the idea. So suppose now we have this, for example, this is a set of chaotic, for example, attractor of a certain chaotic map, for example. And here's how we define a point-wise dimension. Point-wise dimension. Okay. Yes. So just pay attention. So okay. So we have an object. We pick an arbitrary point which belongs to object. So x is one of the objects, one member of the object. Okay. Find a point x on the attractor A. Now let nx epsilon denote the number of the points A inside a ball of radial epsilon about x. So we take an x, we use epsilon as a size of radial. We draw, in this case, we draw a circle. In general, we just draw a volume with the radial of r. Okay, and then we count how many within that volume, how many members are there in the object. Okay, in the object, how many members. So now in general, this n epsilon, which also depends on the x, will scale with epsilon to the d power. Now vary epsilon. As epsilon increase, the number of points in the ball typically grow exponentially. So as we make this epsilon bigger and bigger, more and more number in this. Now when we say we count how many a member in object, the member itself is kind of difficult to define. I mean, for the infinity case, of course, we in principle need to count things into infinitesimal scale. But numerically, of course, we can only count of things of finite size. So this scaling, in fact, is only work for epsilon larger than certain number, certain minimum number. Okay, and then the epsilon itself, of course, will also depend on, if you make this epsilon very big, like if you make this circle is very big, which encloses the whole object, then it's also, beyond that, it's also now the number does not increase. So this scaling is only valid with a certain minimal epsilon and certain maximum epsilon. Not only that, of course, this scaling itself depends on where the x. So the point-wise dimension depends on x. So what we do is we average over all different x. Okay, so average over all different x. Then we get a dimension n, a d, which no longer depends on which x we choose. If we get sufficient number of x to average over, and then we end up this object, this c, is now the scale. It does not depend on what x we choose. And this is what we call correlation dimension. Correlation dimension. Is that clear for you guys, that how this correlation dimension is calculated? It's important because I'm going to have one problem assignment ask you to calculate correlation dimension for logistic map, for example, or for the Lorentz attractor.
Yes, it makes sense.
Everybody, is it clear to you? You given an object, suppose you are able to generate this object. For example, we can generate object by doing Lorentz factor sufficient number of iteration, and then we can create this object, for example. And then you randomly pick a point from the set, and then you count, and then choose a size epsilon, and then you count how many member is inside this size radial epsilon. Okay. And then I average over sufficient number of x, so I get average of that count. And then I change the size of epsilon. That count will scale with epsilon to the least power. So as I change this epsilon getting bigger and bigger, number of n epsilon will scale with epsilon to the d. So you get a plot of log of the c over log of epsilon. Okay, log of c over log of epsilon. Now, as I mentioned earlier, the scaling only works for certain range of epsilon. Is epsilon too small, it does not do the scaling, does not work. If epsilon too big, scaling goes. So there is a region of epsilon where the scaling work. That means that it's a straight line region, a straight line region. Okay, straight line region. And then from this straight line region, you can extrapolate what is d. What is d by fitting this straight line region in, and the slope is basically dvt, and that is what we call a correlation dimension. Again, emphasize it's only work for certain minimum separation and a certain maximum epsilon, which is size of the object itself. So here is actually a calculation of the CE for the Lorentz attractor. Okay, Lorentz attractor with this particular parameter of R sigma and B, R sigma B. For this particular Lorentz attractor, that people, this is back in the 80s, Glasberger and Procassia did this calculation. And they noticed the scaling is log C over log of epsilon, which is IOY naught. This scaling work in this range. And then you get this Lorentz attractor. In fact, you know, this is object is live in 3 dimensions, but it's just barely larger than 2 dimensions. It's only 2.05. So it's object live in 3 dimensions. It got the infinite surface area. It's a finite size. Because it's infinite surface area because it's larger than 2 dimensions, 2.05. So that's why the surface area is infinity. So that is a Lorentz, the correlation dimension of a Lorentz attractor. But same token, we should be able to calculate correlation dimension for logistic map. And so at R infinity at 3.569, the logistic map, the correlation, somebody measured the correlation dimension is 0.5. So there's a region over here, you get 0.5. So logistic map is kind of like a Cantor set. You know, Cantor set, remember, is something which has a finite dimension, but it's live in 1 dimension. Okay, Cantor. So you can appreciate this is look like a Cantor set. So you get a correlation dimension of 0.5. Okay. So you can use this correlation. So if you're using box dimension to calculate, it's 0.538. If you're using correlation dimension to calculate, it's a 0.5. Now it's all depends on how accurate this number is. Okay. So that is a roughly introduction to the fractal dimension. All right, fractal dimension. Anybody got questions? we are done with this chapter. But I'm going to spend next lecture to talk about Mandelbrot set that will actually make this the idea, a concept of fractal, which prevalence in the literature. And here I have a Mandelbrot set itself, which is generated by this code. I will talk about the next lecture, but it's a very beautiful objects. See, I guess I need to run one more time again to show you this up. Is it showing up? Still running, okay? Oh, now it's not showing up. Oh, it's last night was running. You think it's still running? Is it this dark one? You mean the kernel is still busy? It's busy, still running.
It's trying.
Yeah, okay, there you go. It just take a long time. So here is a very beautiful. And the next one is related to it, called Julia set. It's related to a Mandelbrot set. I will talk about exactly what it is, but I just want to show this beautiful picture I generate. This one I did it this morning. It's work. Look at this object. So with that, I think I'm going to stop here. The homework is due now today, right? I hope you all get done.
Yeah.
Okay. And with that, then if anybody, if you have a question, if no question, I'm going to stop right here. Good?
Yep, sounds good.
Okay, hope you all had a nice weekend.
Thank you.
Thank
You
you.
too.
Bye now.
Bye.
Bye.
Bye.